In FOC, when we apply a constant torque to a motor, its speed will keep increasing until it reaches a point where it simply can't go any faster, even if we try to apply more torque. So what actually limits this speed? And how can a technique called field weakening push the motor beyond that limit? In this video, we won't just go through the theory, but also implement it directly and see how it performs in the real world. With FOC, we can control motor torque and speed as easily as controlling a brushed DC motor by adjusting the IQ current. This is because IQ is proportional to torque, while ID is used to control flux and is usually set to 0. As long as ID equals 0, we can focus entirely on maximizing torque. Now let's take a look. When I apply a small IQ current here, the motor starts to rotate. When I try to hold it, it feels very weak and can even be stopped. As I increase the IQ current, I can feel the torque getting stronger. When a motor spins with no load, its speed increases until it reaches saturation. Inside the motor, there are stator windings and permanent magnets positioned close to each other. When the permanent magnets move and we connect a voltmeter to the stator windings, we can observe a voltage being generated. The faster the magnets move, the higher the voltage produced. This is known as back electromotive force, or back-EMF. The main focus of FOC is to control current. Since back-EMF increases proportionally with motor speed, the voltage applied to the motor is also increased by the PI controller in the FOC to maintain the desired current. However, this applied voltage has a limit because the DC bus voltage is limited. At a certain point, the inverter can no longer provide enough voltage to overcome the back-EMF. This is where the motor reaches its speed saturation. To achieve even higher rotational speed, the simplest way is to just increase the supply voltage so that the resulting current can be higher. However, there is another way to increase the current without raising the supply voltage, which is by reducing the motor's back-EMF voltage. The principle is that the back-EMF is large because the magnetic flux in the air gap is large. By reducing this flux, the back-EMF can also decrease. And with the available supply voltage, it becomes possible to produce higher current. We can reduce this magnetic flux by opposing it. Since the ID current is aligned with the rotor's magnetic flux, we can weaken this flux by applying a negative value to the ID current. This is the role of field weakening. The motor speed increases, but the torque will decrease as well. Here, I will try it out directly. I'm using this drone motor with a DC bus voltage of 16 volts. First, I plot the motor speed in RPM, then I set the IQ current to 0.2 amps and observe the motor spinning until it saturates at a speed of 3,460 RPM. In this condition, the ID set point is 0 amps. When I apply an ID current of minus 0.5 amps, the motor speed increases. And as I decrease ID further, the motor spins even faster. This proves that the field weakening theory works. But how do we actually implement it? Is it as simple as continuously reducing ID until we reach the desired speed? Previously, when I first started learning about field weakening, there was one important aspect that I overlooked, which is the voltage limitation in space vector PWM, or SVPWM. In SVPWM, there is a maximum voltage amplitude that the inverter can produce, which is equal to DC bus voltage divided by square root of 3. This means that if the combination of VD and VQ results in a voltage magnitude greater than this limit, it cannot be realized by the inverter. At first, I handled this limitation by calculating the resultant voltage Vs from VD and VQ, and if it exceeded the limit, I scaled both VD and VQ proportionally to keep them within bounds. Mathematically, this approach is correct. However, during testing, I observed behavior that did not match expectations. When Vs had already exceeded the limit and I increased the IQ current set point, the motor actually slowed down slightly. When IQ is increased, the PI controller on the Q-axis raises VQ to generate higher torque. However, because VD and VQ are scaled together, VD also changes. This change in VD alters the direction of the voltage vector. From this, I realized that voltage limitation should not arbitrarily change the direction of the vector. In many cases, especially when field weakening is active, VD should be maintained because it directly controls the flux. Therefore, a more appropriate approach is to calculate the maximum allowable VQ such that the combination of VD and VQ remains within the voltage limit. In other words, once VD is determined, we can compute the remaining voltage headroom available for VQ based on the relationship between VD, VQ, and the maximum limit. This way, the direction of the voltage vector remains consistent and produces the expected behavior, where increasing IQ truly results in higher torque without unwanted side effects, while the system stays within the inverter's voltage limits. Alright, now let's get back to the implementation of field weakening. There are various methods that can be used, and one of the most popular is the voltage feedback control method. In this method, the system reads the resultant voltage from the VD and VQ components that are fed into the SVPWM, and then compares it with a reference voltage called VS-Ref. The difference between the actual voltage and this reference is then processed by a PI controller to generate the ID current reference. At low speeds, when the voltage is still far below the limit, ID remains around 0. As the speed increases and the voltage approaches the limit, the system will automatically inject negative ID current. When I first implemented this method in my code, I observed a rather strange behavior where the ID current was always negative even when the motor was not rotating. After investigating, it turned out that the issue was with the selection of the reference voltage VS-Ref. If VS-Ref is not set correctly, for example, if it is too small or even 0, the system will assume from the beginning that the voltage has already exceeded the limit. As a result, the PI controller immediately outputs a negative ID, even though it is not actually needed. Therefore, VS-Ref should be set close to the maximum voltage that the inverter can produce, typically around 90 to 95% of the DC bus voltage divided by square root of 3. After correcting the VS-Ref value, the system started to behave as expected. At low speeds, ID stays close to 0 because the voltage has not reached the limit. Then, as the speed increases and the voltage approaches the limit, ID begins to move in a negative direction. This weakens the flux, allowing the motor to spin faster. In practice, I still use a trial and error approach to determine the PI gains for field weakening, starting with small gains and gradually increasing them until I achieve a response that is fast enough without causing oscillations. And here is the result when this method is combined with a speed control loop. I limited the ID current for field weakening to -2 amps. Without field weakening, the maximum speed achieved is around 3590 RPM. When field weakening is enabled, the maximum speed can reach about 3,900 RPM. If I increase it further, the motor starts to vibrate abnormally. Then I tried increasing the maximum ID current limit to -3 amps and continued raising the speed. The maximum speed achieved is around 4,300 RPM. From this entire process, we can see that field weakening is not just about injecting negative ID current to increase motor speed. Behind it, there's an understanding of the inverter's voltage limits and how VD and VQ interact with each other. By using the voltage feedback control method, field weakening can operate automatically and adaptively. The system will only activate field weakening when it is actually needed, without requiring manual intervention. Although there is still plenty of room for optimization, such as integrating it with other methods like MTPA, this approach is already sufficient to demonstrate how theory can be practically implemented in an embedded system. Thank you for watching, and see you in the next episode.